Are you being told your attic absolutely needs spray foam insulation? In this video, we're completely debunking this myth and showing you how a foam-free attic can actually be a smarter, safer, and better performing choice for your home or building. Let's get into it. So, before we get into the foam-free solutions that we'll be discussing, it's important to understand why you'd specify spray foam in the first place for a conditioned attic. Closed-cell spray foam provides the benefits of an air barrier, a vapor retarder, and it has a high R value per inch. All of these benefits combined together can help to prevent condensation from forming in an unvented roof assembly. Being air impermeable and a Class 2 vapor retarder, it satisfies the code requirements for an unvented roof assembly. It can also conform to a lot of irregular building geometry and can be applied to hard-to-reach locations to fill in the gaps, making it a really convenient option for an unvented roof system. However, spray foam is not a silver bullet, and there are several reasons why we tend to avoid spray foam as a solution if possible. First of all, spray foam is only effective as an air barrier and for condensation control where it's applied, and that's exactly the problem. There can be plenty of void spaces in a roof where spray foam can be omitted if the spray foam contractor isn't aware of these areas, such as around dormers and shallow intersecting gables. These areas are often inaccessible, which means that the spray foam can't fill these cavities and void spaces, which can result in interstitial condensation and rot over time. The spray foam insulation needs to be installed tightly against the backside of the sheathing for it to work effectively, or these void spaces need to be vented to avoid moisture accumulation. The second problem is that spray foam can potentially crack, violating the integrity of the air barrier and negating the condensation control benefits. We've discussed this before in previous videos, but what can happen is that during the heating season, a small amount of moisture can diffuse through the closed cell spray foam and accumulate in the sheathing, where it gets trapped beneath impermeable underlayments and roof coverings, which increases the moisture content in the sheathing, causing it to swell. In warmer months, the sun heats the roof's surface, rapidly driving the moisture stored in the sheathing back down and out of the spray foam. This rapid change in moisture content causes the wooden components to contract, which can be enough to cause the spray foam to crack from this movement. Once the spray foam cracks, air can leak into the upper parts of the assembly and condense on the underside of the sheathing. But because the closed cell foam is a vapor retarder with a high R value per inch, this condensation has a really difficult time drying out, which eventually leads to deterioration and rot. We've also observed serious off-gassing issues with spray foam on a couple of projects, but more on that in another video that we've had in the works for a while. This brings us to the foam-free solutions. Yes, spray foam makes it a lot easier to have a conditioned attic, but it's not necessary at all if you design the roof assembly in a way that prevents condensation from forming in the first place, and in fact we can get a substantially safer roof assembly using these other strategies that don't have the same kinds of moisture risks as a spray foamed attic. Let's talk about our first strategy. This assembly is a vented roof assembly for a conditioned attic, and yes, it is possible to have a conditioned attic with a vented roof. You have to understand that the attic is the physical space created by the roof framing, whereas the roof assembly is the buildup of components that form the roof system. Now, we'll preface this by saying that this assembly works best with very simple roof forms without any intersecting roof geometry, as we need continuous uninterrupted soffit to ridge venting in order to prevent moisture accumulation on the backside of the sheathing, and that means that every single rafter bay has to be vented. If you do have a more complicated roof, I would either avoid this technique or install purlins that are perpendicular to the roof structure to facilitate cross ventilation. Now, we like to use parallel cord trusses for this assembly because this allows us to maximize the amount of insulation in the cavity space. We've also used I-joists in the past as well, but basically we want to make sure that we have enough space to work with to meet energy codes. If you have a retrofit situation and you're limited on cavity space, we do have a couple of workarounds that we'll discuss later on. So here we have our roof structure. We want to fill that cavity space with a bunch of dense pack blown in cellulose insulation. This will fill all the nooks and crannies in the truss webbing. Now, you certainly could swap that out for a blown-in fiberglass insulation or blown-in sheep's wool insulation, or really any blown-in insulation of your choosing, but we really prefer to use cellulose because it's treated with borates, which not only provides a high level of fire resistance, but also deters mold growth and bugs from making a home in the roof system. The borates leach out into the framing and help to preserve the wood. There have even been case studies with unvented roof assemblies using dense pack blown-in cellulose in cold climates that have resisted the damaging effects of condensation, where you would think that there would be a moisture failure. We take a more conservative approach and still recommend venting this type of assembly, but the preservative effects of the borates in the cellulose and its ability to sequester some moisture without failing and its ability to dry out are reasons why we like using this stuff. Because we're using dense packed cellulose, we need a way to contain that insulation, otherwise it's going to move around and could clog the ventilation space if it gets wind washed. So, on the top side of the parallel cord trusses, we staple some house wrap like Tyvek to the top cords of the trusses, or if you're using rafters or an I-joist system, it can be stapled to the top of those structural members. This will contain the cellulose and prevent it from spilling out, while remaining highly vapor permeable, so it won't impact the drying potential of the roof. Tyvek is around 50 perms, so it'll be vapor open enough to allow moisture to dry into the air gap above, relatively unrestricted. If you are especially concerned about the drying potential of that membrane, there are membrane products like Delta Fox, which are over 100 perms that can be used instead. Now on the top side, we want to maintain at least a 1.5 inch to 2 inch ventilated air gap above the insulation. Cellulose is both vapor permeable and air permeable, and so moisture-laden air that happens to diffuse or leak into the upper parts of the assembly needs a path to dry out. The same is true of any incidental leaks in the roof underlayment. If there's a strong storm and we have water being driven into the fastener penetrations and a small amount of water starts to saturate the sheathing, we want to make sure that the sheathing has the ability to dry out so it can dry downwards into this ventilated air gap. To achieve this ventilated gap, we use 2x4 strapping installed above the top cords of the trusses to form a 1.5 inch air gap and a nail base for the sheathing above. Now, you'll want to coordinate this with the structural engineer so that they specify the right nailing pattern and fastening schedule, but these 2x4s are basically an extension of the top cords of the trusses. Then, we can sheathe over the 2x4s, preferably with plywood, as plywood is more resistant to moisture due to its superior hygric buffer capacity, which just means its ability to store moisture without failing compared to something like OSB. We also want to use a self-adhered underlayment to maximize the water resistance of the assembly. If there is some water intrusion, a self-adhered underlayment won't allow water to travel freely beneath the underlayment since it's bonded to the sheathing, unlike a mechanically attached membrane, meaning that potential leaks will be highly localized. But in general, you shouldn't be observing any problems unless you have an extremely severe storm. Then you can use any roof covering of your choosing over this system. In this case, we just have simple asphalt shingles called out in this drawing. However, metal shingles, standing seam metal, concrete or terracotta tile, or synthetic architectural shingles tend to last substantially longer, so if you really wanted to maximize the long-term durability of the system, choose any of those roof coverings so you don't have to worry about re-roofing for a while. Now, we still have to control air leakage and condensation problems in the roof assembly. Remember that we're using air and vapor permeable insulation in isolation, so we need an interior air barrier and vapor retarder installed beneath the bottom cords of the trusses to stop warm, moisture-laden air from migrating into the upper parts of the assembly unrestricted. So, we've called out a taped smart vapor retarder membrane, which is stapled to the underside of the bottom cords with the joints and seams taped to provide the benefits of an air barrier. Now, I want to stress that its function as an air barrier is the most important aspect of this membrane. The vapor retarding benefits are secondary, as air leakage can transport a heck of a lot more moisture than vapor diffusion alone. We'd like to use a smart vapor retarder for its vapor variable qualities, so if moisture finds a path into the assembly, or if there are some potential condensation drips, we want that moisture to have the ability to dry in both directions. Now, we briefly mentioned that we have another technique that can be used for retrofits if you're limited on cavity space, or if it's too late to change the structural design and you need to meet the minimum energy code requirements. All we have to do is swap out that smart vapor retarder membrane for taped rigid foam insulation. Rigid foam insulation is a vapor retarder, it's airtight, and has a high R value per inch, with some polyiso insulations offering as much as R 6.5 per inch. With as little as 2 to 3 inches of taped polyiso, we can increase the thermal resistance of the roof assembly by R13 to R19 without adding too much additional thickness to the assembly, and it'll provide similar benefits to a taped smart vapor retarder membrane. The difference is that the rigid foam is not vapor variable, and the installation process looks a little different, but provided that you tape the joints of the rigid insulation and air seal the building transitions, the system will work just fine. The next assembly that we can design is an unvented roof assembly using exterior rigid insulation. Now, we've talked about this technique at length in this video, which you can go and watch up here, but with this assembly, the way that we are preventing condensation from forming is that we are warming up the first condensing surface, that being the back side of the structural sheathing, with exterior insulation. By adding exterior insulation to the assembly, we are keeping the sheathing warmer and closer to interior temperatures and relative humidity conditions, thereby reducing the number of potential condensation hours. The more insulation that we install outboard, the closer to interior conditions the sheathing will be. Now, depending on the climate zone that you're building in and the interior temperature and relative humidity that you plan on operating at, you may need more or less exterior insulation. Now, for this assembly, we're using rigid rock wool for our exterior insulation. You can just as well use rigid wood fiber, expanded polystyrene, extruded polystyrene, polyiso, or any other rigid insulation of your choosing, but keeping in line with this foam-free theme here, we're sticking with the rock wool. Now, before the exterior insulation is installed, we want to ensure that we have a robust air barrier in place, installed over the structural sheathing. This will prevent warm, moisture-laden air from migrating through the sheathing seams and condensing in the upper parts of the assembly. If you don't think that this can happen, ask us how we know. We've seen this more than once in both cold climates and hot climates. For the air barrier, we're using a self-adhered roof underlayment, in this case Grace Ice and Water Shield, and we prefer using these self-adhered membranes because they are bonded to the sheathing, which prevents air from leaking through the seams, unlike a mechanically attached membrane. Additionally, when you're fastening the second layer of sheathing or the outriggers to the roof structure through the membrane, if you use a mechanically attached membrane, the torque of the screws will bunch up the membrane, and you'll violate the integrity of that air barrier, whereas a self-adhered underlayment will remain in place because it's glued down to the substrate. Now, we want to connect the air barrier on the roof to the air barrier at the walls. In this case, we're connecting the Ice and Water Shield product to this Blueskin VP100, which is also a self-adhered product designed for wall assemblies. Now, because we have two dissimilar materials, we are taping that joint with a pressure-sensitive acrylic tape that is compatible with both membranes, ensuring that we have a reliably airtight connection. In this particular mock-up, we are forming the overhangs using 2x4 outriggers, which are fastened to the rafters or roof structure below. You'll want to coordinate the fastening schedule and the depth of the overhang with the structural engineer so that they can develop an appropriate fastening schedule for your project. You also want to make sure that the depth of the outriggers matches the depth of the rigid insulation buildup above the roof deck so that the second layer of sheathing is flush across the entire roof assembly. Next, we're able to install our second layer of sheathing. This is our nail base or substrate for the final roof covering, and the second layer of sheathing gets fastened to the outriggers and then through the insulation into the roof structure, where the outriggers terminate and transition to the buildup of rigid insulation. Again, you'll want to coordinate this with your structural engineer, but we use long exterior grade wood screws like the Simpson SDWS timber screws to attach the second layer of sheathing through the rigid insulation and into the roof deck below. The thicker the structural sheathing, the greater withdrawal strength you'll get out of those fasteners. Then, we install a second layer of self-adhered underlayment. In this case, we actually prefer that this membrane be vapor permeable in order to have the ability to dry out that second layer of sheathing. In order to do this, we need a small air gap above the vapor permeable underlayment. To accomplish this, we like to use an entangled mesh mat like cedar breather below a standing seam, metal roof, or metal shingles. This allows any moisture that happens to accumulate in that second layer of sheathing to dry into this gap or drained out of the system. Additionally, having a small gap between a metal roof and the underlayment below will help to prevent any localized corrosion from forming on the metal panels, which can happen especially if you have a zinc roof or a copper roof. Basically, we don't want any water droplets held in tension against those metal panels, otherwise this can cause holes to form in the roof. Now, on the interior side of the roof system, we can insulate the cavities with any batt or blown-in insulation of your choosing. Just make sure that the insulation batts are not foil-faced or vinyl-faced. Foil-faced insulation and PVC are highly vapor impermeable and can trap moisture in the roof assembly. If your local codes are requiring a vapor retarder, use either craft face batt insulation or a Class 2 vapor retarding latex paint on gypsum board. Both have vapor variable qualities, similar to a smart vapor retarder membrane, so they open up if there's moisture present, allowing for drying. Guys, if you found this video helpful, make sure to leave a like and subscribe for more weekly building science videos, and head over to our website at asiri-designs.com where we have over 150 free building science articles that cover a wide range of topics. Links will be in the description below. For now, good luck with your projects. Cheers.